back to Maths with Mrs. J. We're working through a series of videos about integration. And so far we've talked about what I refer to as using the chain rule in reverse when the inner function has just been a linear function. In other words, the derivative of that inner function is just a constant, and we can easily either multiply or divide by a constant without it affecting our differentiation and integration rules. In general, if you get a product or a quotient that you are required to integrate, you want to try and eliminate the fact that it's a product or a quotient. So you want to expand if you can, or divide if you can. The other examples that I want to do with you, however, are to do with these sorts of situations here. Recognizing when you have a situation where you have a power of a function and you have the derivative of that function multiplying it, or some constant times that derivative. Or if you have a function in the denominator and the derivative of that function in the numerator, we can also integrate that. So this one here, using our chain rule in reverse, if we increase the index by 1 and divide by the new index, that will actually work out perfectly fine. Why? Because with our chain rule, bring the index down, decrease it by 1 and multiply by the derivative of that inner function. Same thing here. If we had natural log of a function, you get 1 over that function times the derivative of the function. So most of what we're doing in these examples here is to do with recognizing when we have either a product or a quotient that involves a function and its derivative. Let's do some examples and you'll see what I mean. Okay, find the following indefinite integrals. All right, we've got integral of 2x, x squared plus 1 cubed dx. We should know by now that we cannot just integrate that and multiply the integrals. However, it's kind of cool if we can notice something here. This function here that's being raised to the 3 or cubed, its derivative is 2x. So what we can actually do in this situation here is treat this as if it were just an x. So it's going to be this, increasing the index by 1, dividing by the new index, and our constant term. People are saying, where did the 2x go? You've just forgotten about that. Well, no, I haven't forgotten about that. What would happen would be when you differentiate this expression, you get 4 times that cubed, so the 4's will cancel, and then you'll multiply by that 2x. So that's where the 2x is coming in there. Let's try another example. This one here, it might be better to rewrite it like this. So 6x minus 5 times 3x squared minus 5x plus 1 to the negative 2. Now again, just recognizing here, this function that's being raised to the negative 2, the derivative of this function is sitting out the front here as a product, as a multiplier. So we can perfectly correctly use this, increase the index by 1, divide by the new index, and add our plus c. Now we're going to tidy this up a little bit. This is the same as -1 over this just to the 1, which means you don't need brackets anymore in the denominator. If you're wondering where the 6x minus 5 went, well, no, it didn't just disappear. It would come out when you differentiate this back again. So think about this. This is -1 times that to the -1. The -1's multiply, and you're going to get that to the -2, multiplied by, because of your chain rule, the derivative of that, which is your 6x minus 5. A lot of these questions like this are to do with being able to recognise the derivative either in the numerator or as a multiplier of whatever function it is you're raising to the power. Let's do some more. All right, again, if we have something like this with a square root in the denominator, it's better to change it into index notation. So 6x squared minus 10 times x cubed minus 5x to the -1/2. All right, let's think about this one. What's the derivative of x cubed minus 5x? Let's write it down here. So the derivative of x cubed minus 5x is 3x squared minus 5, isn't it? Now, we've got 6x squared minus 10. That's exactly twice that. Let's rewrite this perhaps using a different colour. So this is the same thing as 2 times 3x squared minus 5 times our x cubed minus 5x to the -1/2. It's okay to have a product, a constant, times that derivative. So now we can go ahead and do our normal thing. We're going to increase this index by 1. -1/2 plus 1 is +1/2. And we're going to divide by that new index. If you're dividing by 1/2, that's the same as multiplying by 2. So we're going to get 4. And this to the 1/2 is square root of this. And again, this hasn't been forgotten about. This would come out when you differentiate using your chain rule. All right, this one here. In this case, we've got our function in the denominator, and it's actually just raised to the power 1 in the denominator. Alarm bells should be ringing in our head to remind us about this. Remember, if we had x to the -1, you can't increase the index and then divide by the new index, or you'd be dividing by 0. So these scenarios are going to involve natural logs. Now, the derivative of x squared plus 1 is 2x. It's just sitting right there for us perfectly. So this is just natural log of x squared plus 1 plus our c. If we want to check if we're right, when you differentiate that back again, you're going to get 1 over x squared plus 1 times the derivative of that, which is 2x. All right, let's do a few more. All right, again, we have a function in the denominator that's just raised to the 1. So alarm bells, we're going to need natural logs. What is the derivative of that? Well, the derivative of the denominator is 3x squared minus 2. Oh, look, aren't we lucky? It's just sitting right there for us. So this one's a nice quick one. Natural log of this plus our c. This next one, Cos on sine, by the way, is often known as cot, but I've deliberately written it as cos on sine here. Cos is the derivative of sine. So this is just the natural log of sine of x, which is kind of cool. So whenever you have your derivative in the numerator and your function in the denominator, you're going to get this sort of scenario happening. Last one. All right, we've got in our denominator e to the x plus 2. All of that's just to the 1. What is the derivative of e to the x plus 2? Well, it's e to the x. So again, we just get this. So just a quick reminder, if you've got a product or a quotient, be on the lookout for the derivative of either the function that's being raised to a power or that's in the denominator, and you might be able to use your chain rule in reverse.